Welcome to this RegEx primer for linguistics. Well, it's a RegEx primer and then there are a couple linguistics examples in here. Okay, so you might have heard the term regular expression, but we're going to look at two definitions to make it very clear what we're talking about. So to the right here, you can see two regular expression patterns. And following this definition by Fitzgerald here, regular expressions are special encoded text strings used as patterns for matching sets of strings. And you can think of these patterns in terms of search terms. So here to the right, we see two examples. W plus meant \B, that's one pattern, and that pattern looks for words or tokens that end with the suffix meant. And then we also have this brackets 0 to 9, curly brackets 4, and that looks for digits with, or for numbers with 4 digits. And we'll have a look at that in a second. Now, a second, more, sophisticated definition, or at least a more comprehensive definition, would be that a regular expression is a specific kind of text pattern. So it's a pattern that you can use with many modern applications and programming languages. So that's important. Regular expressions are supported by most text editors and by most linguistic tools. And you can use them to verify whether input fits into the text pattern, to find text that matches the pattern, to replace text matching the pattern, to split a block of text into a list of subtext, and to shoot yourself in the foot. So the idea is that we can use these search patterns to check whether some text looks like we expect it to look, to find text in a collection of texts, for example in a corpus, to replace texts or to move text around, and to split text based on some rules. And then this last thing here, shoot yourself in the foot, is based on the fact that regular expressions can be very complex and they can drive you crazy due to all of the complexities. However, we're not going to talk about these complexities today. This is just a primer for you to get started, and then you can dive into this topic on your own. Okay, so even without fully understanding what's happening, let's try these two things out. So what you can see here is an online tool that helps you in developing and testing these patterns. And in here, I have a brief excerpt from Wikipedia. And I'm now just going to use that expression that we've just seen. So I've just put that into here, and then down here you can see what has been matched. And this tool is very nice because it explains everything and also lists everything. So think of this in terms of a search. So we've looked for that pattern, and now we've found one match here, and that is development. And that is exactly what we wanted here. Let's look at the other thing, which is this. And this matches all numbers that have 4 digits. So this is very useful for finding years, for example. And we can see here, I've put that in here. This is the text against which this matches, and then we get 4 results, 1936, and so on and so forth. And so this is how these patterns work. And now we're going to look at how these are built and what's going on behind the scenes. Okay, now that we've took a little bit of a deep dive here, let's look at this in a little bit more detail. So a regular expression often looks something like this. And you see these green forward slashes here, and these limit the regular expression. And these are not necessary, but these are often used to indicate that we are looking at a regular expression. And aside from that, the regular expression, or the regex, has a pattern and it has some flags. While the pattern is the main thing, the pattern is the search term, so to speak, the flags can be used to modify that search or to modify that pattern. And here, for example, we are using the flags G and I, and that means that this regular expression is global. That means we are looking for all instances and not just for the first one, and that it is case insensitive, so that we would match, for example, also words that are uppercase and not just lowercase in terms of the meant. And then there are other flags, for example, multi-line if you want to match across lines, and some others. But the most important ones are certainly global and case sensitivity. Okay, so the key ideas behind regular expressions are as follows. A string is a series of characters. And to the right here, you can see that a string, and this is the word string, consists of these characters, and we start counting at 0. That's very common in computer science. So this string has 6 characters numbered 0 to 5. And regular expressions are always working on the character level. So we can't think in terms of words or tokens or anything like that, but we always think in terms of characters. Now everything, and also white spaces and line breaks, are characters. Everything is a character. So for example, if we have something like the idea, we have 3 characters for the, then we have 1 white space character, and then we have all the characters for idea. So we need to be aware of that. By default, regular expressions are case sensitive, but we can use that flag, that I flag, to make them case insensitive. And we build patterns or search terms by combining characters, for example, ment, M-E-N-T, with special symbols. And we're going to look at these special symbols in a second. These special symbols then give power to that whole concept. Okay, so let's have a look at these basic symbols. I'm going through them, or at least through a couple. There are more. These are just some basic ones, and then I'm going to show you some examples. So the first set we need to be aware of are anchors. And these anchors basically help us to navigate within a text. So now think in terms of one text, and that text consists of characters. So you can use these symbols, for example, to look for the start of a string, to do it for the end of a string, or for the boundary of a word. We're going to look at that in a second. Now there are also special symbols for character classes. For example, \d stands for any type of digit. \lowercase w stands for a word character. That is not a word, but a word character. And \upper w stands for something that is not a word character. These are, for example, white spaces and punctuation marks. Now we also have quantifiers. So we can do things like we're looking for that particular letter, for example, but multiple times. And the most common ones here are the star for 0 or more. So let's say a star would be everything between 0 and unlimited a's, plus that would be 1 or more a's. And then there is the question mark, and that's a very important one. That is 0 or 1. And that also makes the expression ungreedy. By default, quantifiers match as often as they can. And by making them non-greedy, by using the question mark, we basically tell them to repeat as little as possible. And so we only capture 1 usually. And we can briefly see that here. So let's say we want to match these 2 quotes here. So we could do quotation mark, dot for every character, now star for a quantifier, and now quotation mark. And you can see greedy behavior here. So the regular expression matches both, but also the and another, because it basically goes quotation mark, all the characters until it finds the last quotation mark on the line. But now if we add the question mark here, we tell it to be non-greedy. And so it stops whenever it can, and then it basically restarts, and so we get these 2 the way we want to. And then we also have the curly brackets, and these are used to match a specific number of times. So for example, an A and then curly brackets 4 would be 4 A's, an A curly bracket 2 comma would be 2 or more, or 2 comma 3 would be 2 or 3, or 2, 2, 3. All right, since we have all of these special symbols, for example, the $sign or the \d, we have also an escape sign, and that is the \. And if we put a \/ before a special symbol, that special symbol is not being treated as a special symbol, but just as a regular one. And so, for example, if we are trying to match stars using regular expressions, we would need to put the escape symbol before the star. Okay, there are also groups and ranges. We've seen one already, the dot, that is just match any character. So it's very common to use .* to do something like match any character 0 or more times. Now we can also do ORs. So if in brackets we do A and then B, A or B, that would be match A or B, the character A or the character B. We can also do ranges, for example, A to Z, would be lowercase a to lowercase z. And we also can do negation by using the negation symbol. And that in this particular instance is not the start of a line symbol, but it's a negation symbol. So that would be look for everything that is not the a symbol. And then finally, we have a number of very special characters. \n indicates a new line. So that is a character in a text that says, here's a line break. We have /r, that is a carriage return. And that is often used, especially on Windows systems, in unison with the new line symbol. So on Windows, you'll see \n, \r for a new line. And then we also have \t for a tab. Again, there are many more of these special regex symbols, but these are the most commonly used ones. And we're now going to look at a few examples to show how these work. Okay, so let's experiment a little bit. If we start by doing a line beginning with this anchor, we can now do something very basic. So let's say we want to match the first word in a string. So we would do a word and then a plus for the first word. And now we match Margaret. Let's say we want to match whatever is last in a text. So let us match whatever, any character, that would be a range, and then the anchor for the end of the text. And now we have matched that very last bracket here. We can also add a modifier here to match any amount of any character and then the end, and then we've matched Wikipedia here. And that is how these anchors work. We can also look at what a word boundary is. So if we just match for a word boundary, nothing really happens. But if we were to do a dot symbol, so that would be any character, we can see that the word boundary then always matches basically the white space here that indicates that a word ends here. Okay, so let's look at different character classes. So a digit is a \d, and we can see now that all digits are being matched, independent of how many characters are in there. We could achieve a very similar result if we did a group or a range in that case, and that range would be 0 to 9. Let's say we only want those with 4, and that's the same example we had before. So in curly brackets 4, and now we are only matching 1936, and so on and so forth. Okay, so that's how quantifiers work. Let's look at another character class, word and non-word characters. A word character is a \w, and now you can see that every single word character here is matched. And now if I change that to an uppercase W, we can see that only the non-word characters, and that is primarily white space and punctuation marks. That's useful if you want to get punctuation marks in that as well. And we'll look at an example a little bit later. Okay, let's look at groups and ranges, and particularly the OR property. So we can do a group, and a group is done by using a bracket. And let's say we want to look for our articles, definite and indefinite. So now we do the OR symbol, and then we do a and possibly also an, and then we close the bracket. And now we are matching all the a's, the, this, and the ands. However, as you can see here, since we are looking for a and an, we also get things like Hamilton or American. We get the a in here, right? So that's not so good. So let's modify that by using word boundaries. So we are going to add word boundaries in front of those and after, just to make sure that we only get these individual words or tokens here. And now we can see that we only get the ones that we like. Let's now look at negation. And if we do negation, we use these brackets, and within brackets, the symbol that's regularly used for the start of the end of a line or string is here now used as a negation symbol. So let's say we want to match everything that is not a, and that is fairly arbitrary, but let's do that. So we do that, and now we can see that everything is matched that is not the character a. Could be useful in some cases. Okay, there are many more variants here, but this should give you a basic idea of how to combine these symbols. And we are going to look at a few useful examples in a second. Okay, a particularly interesting use case is complex search and replace. And now this is a very constructed example, but I hope it'll show what I mean. Okay, so let's say we have this first sentence. There's a cat and a dog, and we want the sentence, there's a dog and a cat. And we want to do this replacement but regex style. So first of all, we do a search. And we do this search with this particular regular expression here. So there is bracket a cat bracket and bracket a dog bracket. And I probably should be a little bit more precise, and these are parentheses. But okay. Now, this is grouping. So we've now created technically three groups here. So the brackets group basically parts of the expression. Internally now, we have the following representation. We have now three groups internally. We have the 0 group, basically, and that is the whole expression, or that's everything that the expression matches. And now we also have these access keys, and we can use the special symbol $0 to access whatever is in that group. We also have groups 1 and 2, and these are the ones that are matched by a cat and a dog. Now it's important to note that these do not contain the regular expression, but these contain whatever is being matched by the regular expression. So instead of there is a cat in brackets, we could also do there is dot star bracket and a dog, and then we would match everything based on that. And then in this group 1, we would have the result, so to speak, or the match of that expression. Okay, and now we can do a replacement. And since we now can access the content, so to speak, of that group, we can replace with something like there is $2 and $1. Let's have a look at how this actually works in an editor. Okay, so here we have VS Code. And now let's type in the regular expression here into the find form. So there is a cat and a dog. That's exactly the one that we've looked at before. Now we could replace that with exactly what we did. So now we can do $2. There is $2 and $1. And now basically if I run this, we will get there is a dog and a cat. Now to exemplify what is meant here, we could do the following. So we're going to remove whatever is in these groups here. And now, instead of writing a dog and a cat, we will make this a little bit more universal. So we are going to use special symbols. So let's go with A. We keep the A, but then we use the word again. And we do the same thing here, \+. And now let's see what happens if I replace it now. So let's see what happens if I replace it now. And basically, we're now flipping it around all the time. Because in the mental table that we now have in our minds, we have these three groups. There is the group 0, that is the whole thing. There is $2, and that is whatever this matches. And then there's $1, and this is whatever that matches. So we could now also do something like, just to exemplify that, we could group 0 here. Then we use the special character N to add a line break. And now let's do that. And now we basically can do something like this. Okay, now let's look at a few useful examples for linguistics. And these are simple, quick, and dirty solutions. Please be aware that there's lots more complexity here. And if you want to have production-ready expressions that definitely do what you want them to do, please have a look at the book and the references, because these expressions work if everything is fine, but they don't take into account edge cases. So I'm going to briefly explain them here, and then we're going to look at them in practice. So first of all, we're going to do tokenization, and we do that by matching words as well as non-word characters. And we do this because we do tokenization here, in which we both tokenize words and also punctuation marks. Now for the second example, we're going to find words with more than 8 characters. And that could be interesting, for example, to find words that carry specific meanings. We're also going to match nouns, so part of speech, annotated tokens in the Brown corpus. Then we are going to look for how to match XML-style tags, for example, to replace tags with nothing or to just remove these tags. And then we're also looking at the more complex variant of this. And we are going to find all of verbs in something like the BNC 1994 XML edition. Okay, so we are going through these examples one by one. So let's start with the tokenization example. The idea here is that you want to get all tokens or words from this text. And we're going to use one way of tokenization, and that is taken from the Natural Language Toolkit. And they use that under the name WordPunct Tokenizer. And the idea here is that we are matching both words as well as punctuation as tokens. And this is being done by using the word boundary here with the plus, and then an OR function. And then we are going to also match for non-word characters. We're going to do this with these brackets here. And the S, by the way, here is white space. So we are looking for symbols that are not a word character and that are not white space. And that will leave us with this list of things here. So these are all the tokens, and we also have the punctuation marks as tokens. That's very useful in many cases. Okay, for the second example, we are trying to match, and that's a simple one. We're trying to match all words with more than 8 characters. So we're going back to the word symbol here, and then we're going to do 8 or more in curly brackets here. And this will give us all the instances of more than 8 characters. Okay, so that is great. You could also use word boundaries here to make this a little bit more robust, but it works quite well. So if you wanted to add the word boundaries here, let's say like that, you would make this a little bit more robust. Okay, so I've changed the text here, and now we are looking at an excerpt from the Brown corpus. The Brown corpus is annotated using this old school inline annotation, where we have a special symbol and then the part of speech tags, at least in this example. And let's say we want to match all the nouns based on this format. So we are starting again with the words, and then we need to escape the symbol because the / is a special symbol in regular expressions. So we are escaping that. And then we are doing NN for the noun. And then because there's variants of that, we are saying we are then taking any other character. And this will now match defendants, police, burglary, and trial. So NNS, NN, and NN. And it's important to use the dot here so that we also get the NN without the additional symbol. Okay, for this example, we're staying within corpus linguistics. And now we have an example from the BNC XML edition, BNC 1994 XML edition. Let's imagine we want to replace or to remove all the tags and just keep the original text. Now we could use an expression that looks something like this. And we're going to look at what it does, and then we're going to look at how it really works. So this expression here will match all the tags, but not the text that is surrounded by these tags. Okay, so how does this work? So we start by opening up basically the tag here with this little angle bracket, and then we are looking for all characters that are not the end symbol of the tag. And then we're just repeating that for an indefinite amount of times using this quantifier. And that will basically give us the tags, including all of the attributes. And that's a very simple way of doing this. Now we can use the very same mechanism to do something a little bit more complicated. So let's say we want to match all the verbs in the BNC XML using that. And in order to do this, we need to access basically the pause attribute here. So part of speech equals verb. Let's do that. Okay, so let's do this in multiple steps. We're going to use the same expression that we've seen a second ago. So let's start by using this. So that's the same expression more or less, but we have included the whitespace character. So we are now looking for basically, again, the tags, but then we have a whitespace. And now you can see we end up basically before the pause because the pause is always the last one in here. And now we are just going for pause equals verb. And now we have that. And now we basically just need to close that off. So we can just do that. And now we need to match whatever is inside the tags here. And then we are going to use the same expression that we used before, although this is a little bit extensive, for the end of the thing, basically. And now we can see that down here, we now have matched all the verbs in this XML with the annotation or with the XML tags. And we could now use the regular expression we've just seen before to basically remove that, or we could do something like that. We could also do a group around this part in the middle. So that is the text that's being surrounded by the tags. Now we could use replacements to just access that group within. Finally, I want to point you to a number of helpful resources and online tools that help you to learn about regular expressions, but also to build them. So we have seen regxr.com, and we've played around with this, and it's a great tool to build these regular expressions. Now, RegEx 101 is a very similar tool. It basically works exactly the same. However, it has a lot of quick references and additional tools here. For example, you have this kind of library here, and if you're looking for a specific regular expression, so for example, you're looking to match dates, then you can find help here in this library, and that is quite useful. I personally use regexr more often than regx 101, but they both work really well, so just use one of them. Now there's also this interesting page that's called ihateregex.io, and that kind of is reminiscent of the fact that while regex are beautiful and while most people generally like working with them, they can also be a pain. And so there's always this double-edged sword here. And with ihateregex, you basically can find good regular expressions for various things. So for example, if you need to match an email, you can just click on email, and then you will get a regular expression that matches that. And they also give you examples and tell you exactly how it works. So that is very useful. And then finally, there is regexlib.com. It looks a bit old school, and it is, but this is a great library of existing regular expressions for almost any problem you can encounter. They also have a nice cheat sheet here, and it's worth browsing this page. Okay, finally, these are the two references, two O'Reilly books. Both are highly recommendable, and if you want to dive deeper, definitely have a look at these. And of course, this was not a comprehensive introduction, but hopefully you now have an idea of how to use them. And I would just recommend using one of these online tools to just play around with these using any text that you like.